We are from Group 3K will present our integrated project. We have been assigned to design a combined gas steam power plant that can generate a total 500 megawatt electricity. Hi, I'm Sara Safiah. I will be presenting about the introduction. Combined cycle power plant use both steam turbine and gas turbine together. The purpose of combined cycle power plant is to produce electricity for consumer use. It is more efficient than single cycle power system, and it can generate 50% more electricity compared to single cycle power system. It can be either single shaft or multi-shaft. For single shaft, both of the gas turbine and steam turbine are connected to the same generator in a tandem arrangement, while for multi-shaft, each gas turbine and steam turbine drives a separate generator. Combined cycle power plant consists of two cycles, which are Rankine cycle and Brayton cycle. Rankine cycle is a steam cycle, while Brayton cycle is a gas cycle. The major components in Rankine cycle are steam turbine, pump, heat exchanger, and condenser, while the major components in Brayton cycle are compressor, combustor, and gas turbine. Next, I will explain about how does combined cycle power plant work. First, gas turbine compress air and mix it with fuel that is heated at a very high temperature. This hot air fuel mixture moves through the gas turbine blades to spin the generator. It produces electricity as well as hot exhaust. The heat produced from gas cycle enters the steam cycle at high temperature through a heat exchanger. Superheated steam at a very high temperature and pressure enters the steam turbine. Then the steam turbine will spin the generator by using the superheated steam to generate additional electricity. After that, the steam is cooled and condensed back to compressed liquid in the condenser. The compressed liquid will flow through the pump that will increase the pressure to heat exchanger pressure, where the working fluid is heated to the saturation temperature, boiled and superheated. This whole cycle is repeated.
Hi, I'm Mabiet Unggang and I'll be explaining the design part. This is our gas cycle design, where ideal cycle that working will undergo in the closed loop is the Brayton cycle, which is made up for internally reversible process. First is isotropic compression in the compressor, second constant pressure heat addition in the boiler, third isotropic expansion in the gas turbine, and lastly constant heat rejection in the exchanger. And this is our steam cycle. For the steam cycle, we use the Rankine cycle model, which is made up for internally reversible process. First is isentropic expansion in the steam turbine. Second, constant pressure heat rejection in condenser. Isotropic compression in pump. And lastly, constant pressure heat addition in the heat exchanger. And this is how combined gas steam power cycle design look like. For the device we use in the gas steam power cycle are 4 steam turbines, 1 gas turbine, 1 pump, 1 compressor, 1 heat exchanger, 1 boiler, 1 condenser. Here are the assumptions made for the calculation.
Hi, I'm Nurin Faqihah and I will be explaining on the calculation part. By utilizing the thermodynamic properties data, the state of the working fluid at steam cycle can be determined as shown. Here are the important data obtained from the manual calculation for the steam cycle as well as the gas cycle. The energy balance for closed system is applied for each cycle where the change in energy of the cycle is equal to Q net in minus W net out. Since the cycle operates steadily, the change in its energy will be zero. Thus, the net energy transfer by work from the system will be equal to the net energy transfer by heat to the system. From the equation, the Q net in and W net out of the combined cycle is equal to 500 megawatt, which is the desired output of this combined gas steam power plant when working under the ideal Brayton and Rankine cycle. The overall efficiency of the combined power plant can be determined by using the formula 1 minus Q out over Q in. From the calculation, the thermal efficiency is 67.4%. The backward ratio of the combined cycle can be calculated by using the formula shown. Hence, the backward ratio obtained is 0.167. This indicates that 16.7% of turbines' work output is used just to drive the compressor and the pump. The amount of coal required can be calculated by dividing the rate of heat entering the cycle with the heating value of coal. Thus, for every second, the amount of coal required is 30.39 kg. The amount of steam generated can be calculated by multiplying the mass flow rate at the inlet of steam turbine with the specific volume at the inlet of steam turbine. Thus, the amount of steam generated is 6067.62 meter cube per hour. To calculate the actual power produced from the combined power plant, the isentropic efficiency of each device is obtained from the references. Then, the actual power produced or used by each device are calculated using the formula. Lastly, the actual power produced by the combined power plant can be calculated and the value obtained is 422.07 megawatt, which is lower than the ideal one. This is because of the presence of irreversibilities in the actual situation.
Hi, I'm Farishah Ainna Binti Rahim, and I'll be presenting about the conclusion and the recommendation. In short, the concept of Rankine cycle and Brayton cycle were used in the calculation to solve the problem in Part A. The combined cycle power plant need to have 4 steam turbine, a gas turbine, a pump, a heat exchanger, a compressor, a condenser, and also a boiler. The amount of backward ratio of the combined power plant is 0.167 and the thermal efficiency is 67.4% with actual work produced of 422.07 megawatt. This proves that the combined power cycle is more efficient compared to a normal gas cycle and steam cycle. However, there are several recommendations that can be done in order to achieve a higher thermal efficiency for the power plant. Firstly, by increasing the temperature of the heat exchanger. According to the Rankine cycle, the higher the inlet temperature of the steam, the higher the thermal efficiency. Secondly, is by decreasing the pressure in the condenser. The low pressure will also lead to the low temperature at the condenser and thus increasing the thermal efficiency. Next, in order to increase the thermal efficiency, use the heat generator and reheater to increase the temperature of the cycle stream. Lastly, increase the pressure ratio at the compressor. Higher pressure ratio between the inlet and outlet stream of the compressor can help to minimize the temperature for heat rejection. This can be proven using the thermal efficiency equation for Brayton cycle. That is all from our group. Thank you.